Today we are going to talk about DSC, which is differential scanning calorimetry. Do you recognize any of those words? Differential scanning calorimetry?
Differential things, it changes or
Change, usually comparative change.
Right. Calorimetry, heat flow, something or other.
Yes. Metry means measure. And calorie is a unit of energy. And then scanning means that some value is changing. Specifically in this, the thing that is changing is temperature. So what we are measuring is how heat and when I say the word heat, I am talking about an energy unit. And how heat affects temperature. Our bodies experience heat as temperature and temperature as heat. We don't have separate sensors for energy versus the temperature. But typically what we are perceiving is temperature, with heat just being sort of this background. So while it feels maybe a little bit counterintuitive to be like, how does heat affect temperature? Those are technically two separate items that both can be studied kind of independent or in tandem with each other. So let's talk a little bit about, we're going to do a little bit of kind of background physics stuff to make sure that you know what's going on here. To start, do you know what kinetics and thermodynamics are?
Kinetics is movement. Something about movement.
Yes.
I don't know much.
That's totally fine. And I think if a faculty member who teaches kinetics or thermodynamics heard my explanation, they would potentially be offended. Because this is such a simplification. But very, very generally, thermodynamics is a yes or a no. Is this reaction going to happen? We talk about favorability, we talk about free energy, we talk about the transfer of energy, but it's kind of like, you could think of it as like the black and white yes or no. Will a reaction occur? Very mathematic, and it works very frequently under ideal circumstances. So we're kind of making these assumptions about how gases are interacting, about how temperature is interacting. And thermodynamics would say that diamonds are unfavorable. Diamonds don't exist, quote, in air, in like normal, like atmospheric pressure. Kinetics takes information related to thermodynamics and is going to tell us whether that favorability is going to actually happen. So kinetics has to do with time-related questions. Thermodynamics would say diamonds are unfavorable at atmospheric pressure. Kinetics says yes, but it takes so long for them to transition out of a diamond state that it functionally is stable for us. So kinetics is going to be more time-related. Reactions. It's going to be very physics related, where thermodynamics is going to be very math related. And it's not to say that thermodynamics is not real world, but kinetics takes into account a lot of real world situations. And not to say that kinetics doesn't make its own simplifying assumptions. And that's why I don't want to make any faculty mad, because that is a huge simplification of 2 semester-long classes. Like, there's a lot more content than that. But very basically, when we're talking here, we are looking at thermodynamics versus kinetics. Thermodynamics being, is it going to happen? Kinetics asking, how quickly? And we're going to come back to why that distinction matters. Next question. What do you know about, well, actually, let's see. This is related to thermodynamics. Yeah, we'll call it the same thing. State of orange. So in thermodynamics, there are a couple of ways that we can classify reactions. We have endothermic. And we have exothermic. Quick overview of endothermic versus exothermic. Do you know?
Endothermic is heat is a reactant, exothermic is heat is a product.
Yes. Endothermic, and another word would be the sample is absorbing heat, or the reaction is absorbing heat. Exothermic would be expelling. It's producing heat would be exothermic. Another way we can organize our reactions is repeatable versus non-repeatable. And I'm making a little like 4x4 here. Because repeatable and non-repeatable are not different than endothermic and exothermic. They are another category of the same reaction. One reaction can be both. Pretty proud of those straight lines, not gonna lie.
That's good.
Thanks, grid. Can you give me an example of or I guess really quickly, do you understand what I would mean by a repeatable versus a non-repeatable reaction?
Something that you can go one way and then go back.
Exactly.
Versus
Yeah, we're talking about, is this repeatable or not, by reversing the temperature change. So if I have an endothermic reaction that absorbs heat, if I then cool the thing back down, is it going to undo the whatever reaction it just went through? Can you give me an example of one or the other?
Ice melting and then freezing again.
Exactly, so that's repeatable because we can go melting and then freezing. Do you know if melting is an endotherm or an exotherm?
Melting would be endo. Wait, yeah.
Yes, yeah.
Endo.
So we're going from a low energy state, which is a solid, to a high energy state, which is the liquid, which means that I increased in energy, meaning it took energy in. I gained energy.
Yeah.
So a repeatable endothermic would be a melt. Also continuing in that direction of temperature, assuming that our system is like fully enclosed, we would have a melt or evaporation is also endothermic repeatable. And I'm going to put a little asterisk next to evaporation because it's only repeatable if it's a closed system. Like, yes, by cooling it down, you're going to get the evaporated water, the evaporated, like, steam back into water, but only if the steam didn't, like, escape and fly away. Yep. Exothermic would be going the other way, so that would be crystallization, or also known as freezing. Or condensation. And I'm going to put, yeah. Minor anecdote. You know how in math and like physics textbooks, they've got these little like stories at the beginning of the chapter, and like the story kind of introduces the theme of whatever the chapter is. I was really bad at listening to teachers through all of my public education, and also some of my, university education. And I loved to read those chapter stories as a way to keep my brain engaged in class.
Okay.
And this one, I don't know why, has stuck in my brain for all of the years since I graduated. It was a story about a freeze in California, and it was, I think it was too early in the season. They hadn't yet harvested all of the orange crop on the trees in the orchard. And it was getting colder and colder, and they had like lit fires around the orchard to try to like keep it warmer. But the temperature's dropping, and they're worried that it's gonna damage their whole crop. And so what they end up doing is they spray the trees down with water, because the water freezes, and freezing is an exothermic reaction, meaning when the water freezes, it releases heat into the oranges that it's encased, and having a layer of ice on the outside of the oranges protects the crop, and everyone is saved, and math or physics, whatever this textbook was, wins again.
Interesting.
So it feels very counterintuitive to be like, yeah, freeze is an exothermic reaction. You're like, no, that feels cold to my hand, but it is minorly releasing some heat. This one's a little harder for everybody. Can you think of any examples of a non-repeatable reaction? Endothermic or exothermic?
Burning something?
Burning something, absolutely. Depending on the reaction itself, that can be absorbing heat or releasing heat, depending on what is burning. Have you ever seen someone take a chunk of potassium and throw it into a lake? Not in person, on YouTube. I would not recommend doing that in person.
Okay.
It's a very reactive reaction. It's very excited. It's a very big reaction.
Okay.
And it basically blows up. It's big explosion. That's going to be an exothermic reaction. So potassium into is not really what I'm talking about here. Potassium plus water. That's really iconically explosive. If you're looking for a good time,
Okay.
Google potassium or sodium being thrown into water.
Okay.
Real sketchy, super cool. And I think the hardest in all of my years of teaching this, the hardest that I've seen for people to do is a non-repeatable endothermic reaction, which is funny because we do it every single day, cooking and baking. Anytime a protein from an egg cures from its soft state to its hard state, we're adding temperature to the system, and there's no amount of freezing that cooked egg that's going to revert the proteins back to their previous state.
Interesting.
And we kind of already talked about this, but I just want to reiterate that when I'm talking about non-repeatable, some of these things can be undone. If we're talking about Jell-O, I don't know if that's endothermic or exothermic, but Jell-O sets. And it sets by going from hot to cold. And there's no amount of leaving it out that's going to reverse. But if you get it really hot, you kind of go
Right.
beyond, you can kind of reverse it. So there are some things that are kind of this like weird like kind of reversible, kind of not. You could maybe like, there are some things that we say are non-repeatable or non-reversible, that you maybe could technically reverse by putting in a lot of effort. But in this case, we're specifically talking about, can you reverse it by just changing the temperature back to what it was before, cooling it back down.
Okay.
A really easy rule of thumb for figuring out if something is endothermic or exothermic is that if we are that's a really terrible sentence I've written in my own notes. If you are increasing the temperature, so that would be like melting, evaporating, it's probably endothermic. If you're decreasing the temperature of the system, the reaction is likely exothermic. And that would be things like crystallization and condensation. This is a rule of thumb. This is not a blanket statement. These are just like, that's one thought. Another rule of thumb is if you are breaking bonds, it is often exothermic. And reverse, if you are creating bonds, it is endothermic, like baking with an egg. Okay. Any questions on kinetics, thermodynamics? Really brief overview there?
Nope.
Okay. Let's talk about a property of materials called heat capacity. Have you learned about heat capacity?
Not much. A little bit.
Great. This is one of those things that I studied mathematically over and over and over in a bunch of classes. But I didn't understand kind of the real world application for quite a bit longer than I was taking those classes. So I'm going to approach it from the real world side of things because I am not a math teacher. So heat capacity is, and this is the definition everybody will give you, the amount of energy that it takes to raise the temperature of a material. The language of this definition might feel a little familiar because differential scanning calorimetry is studying how heat and temperature are related. And I just told you that heat capacity is how temperature and energy, which is heat, are related. So very entwined in this discussion today. Functionally, what this means is, let's say I have 1 gram of water sitting out in like a bowl. Here I've got like I'll put like a droplet of water. And I have 1 gram of copper, which I have written in my own notes is about 2/5 of a penny. I don't know why I calculated that, but it's there you go. Water has and I'll draw like, how do I draw 2/5 of a penny? I don't know what I'm doing here. We'll say like 2/5 of a penny. There's a little face on it. Water's heat capacity is 4.18 joules per gram degree Celsius. And we are going to go into what all of those units mean. I'm not going to just like throw units at you and expect you to know what's going on. Copper, assuming this is like a pure chunk of copper, its heat capacity is 0.385 joules per gram degree Celsius. What this is saying is that it takes 4.18 joules. That is an energy measurement. When I'm talking about heat, joules is my unit.
Okay.
For 1 gram of material to be raised by 1 degree Celsius.
Gotcha.
on the flip side, if I want to get copper, 1 gram of copper raised by 1 degree Celsius, I only have to put about 1/3 of a joule into the system for that to happen, rather than adding 4 joules. So in this example, if the water has raised, let's say I put them both in the sunshine, and I notice that the water is raised by 1 degree Celsius, the penny is almost 11 degrees hotter. And that's because there's like 0.38 up to like 4.18. If you divide those out by one another, it's a 1:11 ratio. 1:11 takes 1 of these to raise 11 of these. So that is the real world application, is like, why does my seatbelt burn me in the summertime, but the water in the water bottle still feels like not boiling hot? And it's because the water has the capacity to hold much more heat without its temperature changing, where the seatbelt, the piece of metal, has a much lower capacity to hold heat without the temperature changing.
Gotcha.
So the penny is going to be quite a bit hotter than the water. Does that make sense?
Yeah.
Okay. There are 2 different there's a whole bunch of different units. This one I have energy per gram degree Celsius. I could just swap in degree Fahrenheit if I was a lunatic, or Kelvin.
Okay.
So we can change that unit to be increased by 1 degree Kelvin. It's not a degree, 1 unit Kelvin. I could use, instead of grams, I could say per mole of the material. Or I could say per pound of the material, again, if I'm a lunatic. So I can change those units. I think joule is pretty much always the unit, but there are other energy units as well, and joule is not necessarily the only unit. So this 4.18, you'll sometimes see people write very different numbers, and it's just because they're different, using different units, and we're converting between Celsius and Kelvin or whatever. Okay. So just be aware of that. Make sure your units are proper. When we are talking about heat capacity, you will see people use 2 different phrases. One of them is just straight heat capacity. Heat capacity is called an extensive, extensive property. Have you heard that language before?
No.
That means that it is not material specific, that it is sample specific. So what I'm saying is this penny in my hand right here.
Okay.
The unit on this one is joules per degree Celsius, or joules per Kelvin, or any combination of those values. But you'll notice that it doesn't have per gram, because in this case I don't care about how much material. I am talking specifically about this thing in my hand.
Okay.
Takes whatever joules per degree Celsius.
Gotcha.
So in this case, we're not specifying any sample properties because the property itself is sample specific. I am not able to apply the values of this penny to the values of another penny. They're going to be different, likely, because they are their own things. Maybe this one has a gigantic scratch through it and it's missing some mass. But when we're talking heat capacity, that doesn't matter because I'm talking about the scratched penny.
Okay.
So this can be a single pure material, like a pure copper penny, but this also could be something as complicated as a building. And a building has got carpet and wood and metal and cement and glass and a ton of different materials in different quantities. It'd be really hard to be like, joules per gram degree Celsius for a building.
Right.
Because there's no such thing as like a gram of a building. There's nothing I can do to extrapolate that to a bigger building. A bigger building is going to have a different composition and therefore a different heat capacity.
Okay.
So there are some uses for heat capacity, but the more useful value is actually specific heat capacity. Specific heat capacity, then, if we were talking about heat capacity being an extensive property, specific heat capacity is called an intensive property. Meaning it is material specific. This is the one that is joules per gram degree Celsius, or joules per gram Kelvin, or whatever else, per mole, per pound, per nanogram, I don't know, whatever.
Okay.
What's nice about this is I can scale this up. This does have to apply to a pure material. I couldn't do a specific heat capacity of a building, but this would be something like I have a piece of copper, I have water, I have the cement bricks that I'm building this building out of. Any pure material, I can take this value per gram, and then I can look at my big old pile of bricks that's like 800 tons, or I can look at my one tiny brick that's just a couple pounds, and I can figure out what the heat capacity is because I know the specific heat capacity.
Gotcha.
And I did use my language deliberately there. I can calculate that extensive property, this heat capacity of one specific item, if I know the specific heat capacity that applies to all the items.
Okay.
Does that make sense?
Yeah.
So this is normalized typically, like I said, by sample mass. You can normalize it by something else, but it needs to be something that can be applied to a lot of different materials kind of across the board. Okay, specific heat will often change when a material changes phase. So when water turns into steam, water and steam have different heat capacities, specific heat capacity in this case, because I'm talking about a material, not an item. Oops, I'm gonna go back to my blue. So like you're going to see a difference in heat capacity when the phase changes. So when we're talking about water, I am talking about maybe liquid water, not the same as ice, not the same as water vapor.
Right.
And then I'm gonna add one more little review kind of item. Have you learned about glass transitions?
Nope.
Cool. A glass transition is when a plastic gets cooled down and turns into this really hard, almost glass-like brittle state. So if you think about if you've ever put a Tupperware in the freezer and you pull it out and it cracks, it has gone below its glass transition temperature. And just like melting or boiling, there is a temperature for most materials, and we're talking polymers specifically. There's a temperature at which they will transition into this glassy state, just like there's a temperature at which ice will melt. That change is actually not a phase change. There's not a significant absorption or like it's not an exotherm or an endotherm necessarily. It is more a change of heat capacity. So the thing that changes is not necessarily like it releases a bunch of heat and now it's in a glassy state. Apparently my window is having a bad time. Which is why it's not the same as freezing. So even though it appears like freezing, where we went from sort of the softer state to the harder state, we were a solid all the way through that. We never went from solid to liquid.
Right.
So it's not exactly like a freezing, melting kind of interaction. It is definitely not an exotherm or an endotherm. And we're going to talk about that in a little bit, but really it's just a molecular rearrangement. That leads to a change in heat capacity. And heat capacity is written C with a P, a sub P, like this.
Okay.
C sub P. So there you go. All of this stuff was sort of review oriented because it's all going to be studied using a DSC.
Awesome.
So now that we understand some of this nonsense here, let's move on to how a DSC works, the data we collect, etc. So let's study water, and I was going to use red, but water is a blue color, but I just used blue, so we're going to do purple because that is the blue of the secondary colors. So we're going to study how an ice cube changes with heat. I don't know why I drew that ice cube the difficult way, but I did. There we go. There's the easier way to draw a little cube. Boop-a-doop-a-doop. Okay, and I'm gonna scoot that over just a touch. So I have an ice cube here. And do you know what temperatures at which this ice cube is stable, not changing, no melting?
0 to 32.
Yeah, what unit are you talking?
Celsius. I guess it can be below 0 too.
So 32 is the Fahrenheit equivalent of 0 Celsius, which is probably why 32 exists in your head.
That's why I was, yeah.
An ice cube, yes, so you were right. An ice cube can be negative infinity degrees up to 0 degrees Celsius. How are we going to do that? We'll say right here is 0 degrees Celsius. And down here is negative infinity degrees Celsius. We could talk in Fahrenheit, we could talk in Kelvin, but we've got like the melting temperature of water in this whole range right here, we are perfectly stable. The ice is ice. It is a solid, it is not changing. It's colder or it's warmer. But as far as where the molecules sit and how they're reacting with each other, there is not a change. What starts happening at 0 Celsius?
It melts.
It melts. So let's imagine, got a helicopter going overhead. That's not an imagining, that's actually happening. Let's imagine that I have this ice cube and it's negative 50 Celsius. I am going to add a little bit of heat to this ice cube. I'm at negative 50 Celsius. Do you know what's going to happen to the temperature as I add heat? Remembering that heat is another word for energy. I'm adding energy to the ice cube. It's at negative 50. What's going to happen to the ice cube?
stay the same.
It will not stay the same temperature, but it will stay the same phase.
Right.
So it's going to stay an ice cube, and the temperature is going to rise. This is heat capacity. How much energy or how much heat do I have to add for the temperature to start rising from 50 degrees Celsius to 49? Negative 50 to negative 49 to negative 48, etc.
Okay.
So this right here, heat capacity, we're solidly in heat capacity zone right here. At 0 degrees Celsius, as I'm adding this heat energy, the ice starts to melt. Thermodynamics says, though, that ice cannot exist any hotter than 0 degrees Celsius. But I'm still adding heat energy. I'm adding energy, but I'm no longer getting this same, outcome. I'm no longer getting an increase in temperature because ice doesn't get hotter than 0. What happens here, even if I add heat and the temperature stagnates, that looks like a plus. It's a T, I promise. And I'm realizing I probably should have written temperature with a capital T because that is what the world has decided. Temperature is a capital T. It's just the rules. I don't know. I don't make the rules, I just follow them. If the temperature stagnates, do you know, energy can't be destroyed? Nothing's I can't just, disappear all that energy. I'm shooting it right at the ice cube. The temperature's not changing. So what is the heat doing? Where is that energy going?
Going to the phase change.
Going into the phase change, yes. So I'm going to add plus transition because all of that heat is being absorbed by the ice molecules because this is an endothermic reaction. Look at that. More backstory that ties in here. Eventually, good? Okay. Eventually, all of that ice is going to melt and I have now water. Need that alarm to stop going off. When is our next phase change for water? Do you know?
100.
100, yep. 100 degrees Celsius, which is actually really convenient. Water has this very nice 0 to 100 scale.
Right.
What percentage of hot is this water? You're like, it's 87% hot. And you're like, wow, that's real dang hot.
Yeah.
And then you're like, actually, it's 0% hot. And you're like, wow, that is almost no water hotness. On the flip side, Fahrenheit is people percentage. So 0% Fahrenheit, 0 in Fahrenheit is wow, that's 0 warmth. But survivable as a person. And 100 Fahrenheit is wow, that is all of the hot. And you're but survivable. And then random days in the spring and the fall, you're it's 50% hot. And you're yeah, that's halfway hot.
Yeah.
So Fahrenheit is people, Celsius is water, Kelvin is electrons, so that's not worth talking about. At 100 degrees Celsius, I am going to start getting evaporation. So I'm going to draw some little, gas molecules, I don't know, dots above. While the water is just water between 0 and 100 Celsius, as I add heat, what happens to my sample?
Temperature goes up.
Yep, increase temperature. At 100 C, we are going to see the same thing that happened at 0 Celsius. I'm continuing to add heat. The temperature stagnates. And we have a transition. And all of the heat energy that's going into the water is being converted into transition energy for the steam. Because again, evaporation is an endothermic reaction. It's absorbing that heat. And then up above it, I have just like steam, and ignoring the fact that like plasma is technically a thing. We can go, up and up and up and up and up in temperature, and steam is just going to continue being steam. It's just going to be really hot steam. This is the reason why steam burns are so much worse than like water burns, because steam can get so much hotter than water can. So be careful when you're opening the pot lid to your mac and cheese. That is the danger. Oh, I meant to say this earlier, speaking of cheese. Glass transition temperature is when something goes from hard to soft. And everything is always like solid. There's still solid particulates. It's not melting. Cheese doesn't melt. Cheese goes through a transition temperature rather than a true melt, because the solid particles are still intact. They are just flowing past each other instead of like turning into a liquid. So that's kind of a weird thing. Melting cheese is not a phase transition as much as it is a like a glass transition.
Interesting.
Type thing. Anyway, so there's a fun fact for parties. Very exciting. Okay, any questions about what's happening here?
Nope.
Let's recreate this then inside of a DSC. So the setup of a DSC is I have 2 crucibles. Each crucible is sitting on a sensor. And these are temperature sensors. I have 1 crucible that is my reference. I'm going to put an R for reference kind of up above that. The other one is my sample crucible. And these crucibles are typically made out of like aluminum oxide or aluminum if you're doing lower temperatures, or sometimes like platinum. And there's all sorts of other types. But something that is going to be thermally stable over the temperature of interest. So the crucible is ideally not going to change at all. And I am going to fill some sample material into my sample crucible. And then I am going to surround it with basically like a furnace, heating coils. I don't know why I said basically a furnace. It is a furnace. And that furnace provides heat energy. Okay, so that furnace is providing heat energy. The sensors underneath the pans are measuring the temperature. And ta-da, we have a DSC. We can compare how the temperature changes in my reference versus how it changes in my sample crucible. And I'll go through that a little bit more specifically. But the furnace is going to provide energy at a set rate. Typically that's going to be like, the furnace is going to increase by 10 degrees Celsius per minute, or something along those lines. But I have this very regular addition of heat energy, very similar to up here, where every step of the way I was adding heat, and it's doing that at a very constant rate. What we would see if we were to plot the temperature of the reference with relation to the temperature of the sample. Probably should have color coded these a little better. Reference. And I'm going to use orange. Sample. If there is nothing in the sample cup, and I were to plot, let's say, furnace temperature versus temperature sensors. I know that the furnace temperature is increasing linearly, right? It's increasing at some like well-known rate, 10 degrees per minute being common. Assuming that there is nothing really going on here, the temperature sensors are also going to see pretty much the exact same increase in temperature. They're going to follow each other. And whether that is the reference or the sample, both of them are pretty much just gonna like, I add 10 degrees Celsius extra energy to the system, and the temperature sensors say, yes, you did. So we've got a very close kind of match here. Let me just scoot that over, and I'm going to duplicate that next door so that I can specify this is with that's with an empty sample cup.
Gotcha.
Assuming that I have filled the sample cup, I'm going to get the same reference line, and I am a human being, so those slopes are not the same, but they should be. Probably, if I copied it, I probably should have kept the orange, or I probably should have just tried to erase the orange line and kept the green line, but oh well. Here we are. And we know that my reaction, assuming, let's say, we're doing this reaction right here, where we start at very cold, we melt the ice, and then we go up to fully melted. I have different parts of my reaction. So let's say the temperature here, let's say this is what we call T melt. So that would be like 0 degrees Celsius, right?
Okay.
I have my orange and my green exactly backwards from what my own personal notes have, so that's really fun. I didn't even mean to choose orange and green. My sample, as long as there is something going on, we're going to follow temperature pretty closely. Now, heat capacity, if the material has really high or really low heat capacity, that is going to change the offset on this. So the sample may actually do something like this, where it initially does absorb a little bit of heat before it starts increasing in temperature. So that does happen. But my sample is going to continue increasing in temperature until we reach our melting temperature. Just like we talked about when we were talking about the ice cubes, at that point the temperature of the material stagnates, meaning my orange line now goes horizontal, and it should be on top of that gray line, but I am making it slightly different for the sake of being able to see both lines. At the end, when that reaction is finished, so I'm going to put a little line here. At the end of the reaction, whenever that is, all of the ice has turned to water because, it was melting for long enough, and the kinetics and the thermodynamics all said, be liquid now. You'll notice that I have this very big temperature discrepancy between the furnace. The furnace temperature is way up here, or the reference temperature, which is basically the same as the furnace temperature. But my sample temperature is way down here. So very, very rapidly, the sample is going to increase in temperature. And then it's going to kind of resume its a linear path upward.
Okay.
Does this make sense?
Yeah.
So far? Okay. So at some specific, and we could put this x-axis because we know, sorry, I started like 3 sentences without finishing a single one of them. Because we know that the furnace temperature is increasing at some linear rate, I could set this to be time just as easily as I could set it to be furnace temperature.
Okay.
So this could be timeliness of the reaction instead of temperature of the furnace. So that's not particularly hard to make that. But what I have is from here to there, I have the time, how long it took for that reaction to occur. I also can get a little bit of information about from when the reaction ends to when it rejoins kind of the temperature slope. I can get a bit of information about that as well. And then what we do is we take this, we kind of flip it on its side, so we turn it, and we subtract this straight reference value right here, this green line, from the sample line, and we get a line that in reality looks like this. My x-axis is going to be either time or furnace temperature. And my my y-axis is going to be heat flow. Goodness. And the unit for heat flow is going to be watts, typically, which is a unit of power. And power and energy and heat are all closely related with just some fairly straightforward conversions. So we're not that far from where we wanted to be. A lot of times it will be watts per gram, and it's actually going to subtract out the gram amount of material, of sample, that you put on the crucible. So we're kind of doing a specific heat flow instead of just like a generic heat flow, going back to our specific heat capacity and heat capacity values. And our graph is gonna look something like this. I am a person, so my baseline is a little bit squabbly there. But the idea is like we should have a hopefully fairly flat background. I just drew it wonky. On this peak, I can label a lot of the same stuff that we labeled on the beginning of the peak. I can label the start of the reaction. It's not quite it. Yeep. And we call the start of the reaction the melting temperature or the evaporation temperature. It is the reaction temperature. When you look up a table of values and it's like water melts at 0 Celsius, it's the beginning of this DSC peak. We also have here where the reaction was happening the fastest. So that's the very tippy top of the peak. And we can also mark the end of the reaction. And between those two, we can get sort of like how long the reaction took. So you can see a lot of the stuff, a lot of very similar data in this. Like, this is what we actually see, this black graph that I've drawn here. This is what the instrument will spit out and what we will process. But it's getting that from the green and the orange that I've drawn above. One other fun little bit of information is that we can take the area under the curve, and that is the enthalpy in, well, struggling. Enthalpy. Enthalpy of the reaction is the quantity of energy absorbed or released over the course of the reaction. So
Okay.
this is how much heat did that freezing water release into the oranges. This, what I've drawn right here, could be an endotherm, could be an exotherm. We were talking about a melt, so it was an endotherm. But we have not chosen a specific direction to indicate exotherms and endotherms when it comes to DSC data. So often on the y-axis, you'll have a little sign that'll say exo down. So it'll have like a little arrow on it, and it'll specify that if anything is pointing down, it's exotherm. In this case, ours is pointing up, so it must be an endotherm. So the axis will tell you it's not a positive, negative, peak facing up, peak facing down. I could just as easily turn this whole graph upside down and it would be equally valid. What matters to us is this little exo up or down. The reason we haven't really picked a direction is because you can imagine, like, are we talking about heat coming from the sample or heat coming from the system? And heat is flowing out of one and into the other. And so there isn't an empiric, like, positive, negative direction when it comes to thermodynamics. We just have to define that for ourselves. And in DSC, that is how we choose to do so.
Cool.
Okay, any questions up to this point here?
No, all good so far.
Okay, awesome. I talked about heat capacity. Nope, we'll get to heat capacity in this conversation, but I talked about glass transition temperature a minute ago. So glass transition temperature, I mentioned, is not necessarily an endotherm or an exotherm. So you're like, so what happens during the test? How does that look? Going back to my DSC, kind of like the raw data lines, and this is specifically for glass transition right here. A glass transition is a change in heat capacity. Heat capacity has to do with, like I said earlier, that displacement along the x-axis at the beginning of the test. So I have my material following linearly. That was, approximation at parallel. At the glass transition temperature, it'll maintain temperature for a second and then continue onward. So I've got a heat capacity change here. What that looks like, actually I should have drawn that square so that I could fit other things next to it. I'll stick that down here, and we're going to draw, this is what we would actually see out of the instrument. Time, heat, flow. And again, this totally depends on if you are endotherm up or endotherm down, but the data will look something like this. It'll be what we call an S-curve or an inflection point. And an inflection point is where we change from concave one direction to concave the other direction. Or you could say like concave to convex. In this, I have the onset and the offset, right? Just like before, I have onset and offset. And the difference between those two lines is the change in heat capacity. I'm drawing everything much too close to each other. This is technology. There's infinite vertical room. Why squish everything all together? No reason. Okay, so that was just to bring back glass transition. You're not going to see glass transition always in DSC. DSC is not the best method for determining glass transition. A better technique for glass transition would be something called DMA, or dynamic mechanical analysis. We do have a tool that can do that, but that's a whole, separate discussion.
Okay.
But DSC can do glass transition well enough.
Gotcha.
All right, last couple things to talk about here. Let's talk about some special considerations when we're setting up a test. And I don't think I've used green yet, not for a section anyway. So that is a very green. That's better contrast. Okay, so let's talk about heating rate. Do you remember what I said about our normal heating rate?
No.
Our normal is 10 degrees Celsius per minute. And the scientific community has generally decided that 10 degrees Celsius per minute works for most materials. The reason is because there are pros and cons for going faster and slower. And we've just all sort of settled on 10 degrees per minute being the one we use. As a point of information, some softwares will talk about instead Kelvin per minute. And you might be tempted to convert Celsius to Kelvin in order to convert Celsius per minute to Kelvin per minute. But it's important to note that even though Celsius are, 20 degrees Celsius is the same as 300 Kelvin, if I increase by 1 degree, so I have 21 degrees Celsius, that's the same as 301 Kelvin. So these are linearly related.
Okay.
So 1 degree per minute is the same whether you start from 300 or you start from 20. So that can be a little bit confusing for people because they want to try to convert between Celsius and Kelvin. But that is the same as 10 Kelvin per minute.
Perfect.
So just be aware of that. Don't get looped in. So let's take our two options. I can go faster and I can go slower. If I go faster than 10 degrees per minute, I'm going to have severe thermal gradients. Think about if you take an ice cube and you were to plunk it in the oven really quickly. The middle of that ice cube is going to stay 0 Celsius for a long time while the outside melts. And it's going to look like the temperature or the reaction is happening at a different time scale than it would if you were to just leave it at 1 degree Celsius. It's going to react very differently.
Right.
We also have the potential that the ice is going to crack. And now I've got two pieces. And so I've got a thermal gradient in each piece, and maybe one's gonna finish melting faster than the other. So my temperature's gonna change on one side of the pan, but not on the other. It just kind of turns into a mess. So thermal gradients in our sample, not ideal. So faster is not great. We would have also exaggerated kinetics. So that is where like the ice cube is going to melt quite a bit faster in a furnace than it is at 1 degree Celsius. But that doesn't necessarily mean that that is usable or important data. So the kinetics, the time-related bit of information, is going to be really significant. And if your oven is preheating, which is what our furnace is doing, right? It's constantly increasing in temperature. The temperature reads 400 Fahrenheit. I don't actually know baking in Celsius very well. But your oven reads like 350 and then 375 and then 400. And you're like, well, my ice cube hasn't melted. So ice must melt at a hotter temperature than 400 degrees Celsius. We know for a fact that that's not true, but because the kinetics are trying, like the thermal gradients, and the ice is trying to keep up with the temperature, but the ice is going to last at a really high temperature. That's going to make it look like its melting temperature is much higher than it truly is.
Okay.
So that's exaggerated kinetics.
Gotcha.
It's going to appear as though our melting temperature is way different than it truly is. So neither of those particularly ideal. If we are going much slower, the reactions are happening with very little driving force. So let's take the opposite. I take that ice out of the freezer and I put it at 0.5 degrees Celsius. We are technically above its melting temperature, and it will technically begin to melt. But it's going to take a very, very long time for that to happen. And the energy being absorbed by the system is happening tiny little packets of heat at a time. There isn't a lot of heat for the ice to absorb. And so we're going to get decreased sensitivity because the ice is melting so slowly that unless we have a really sensitive detector, it's not going to notice, oh, hey, the ice is actually getting warmer.
Gotcha.
So there are some reasons we'd want to go faster, some reasons we maybe want to go slower. These are the cons of each one, and the reason why 10 degrees per minute has been sort of chosen as our middle ground. Tends to be fast enough to give us enough driving force. Reactions are happening fast enough that I don't have sensitivity issues, but they're not happening so fast that one part has finished reacting and the other part is still frozen, like sublimation, which is going from liquid or going from solid to gas really rapidly. And the kinetics, it's not going to appear as though the ice is melting at a much higher temperature than expected.
Right.
So 10 degrees per minute kind of balances those things out. Any questions on choosing a heating rate?
Nope.
Okay. Sample mass. We typically choose 10 milligrams to run DSC on. Milligrams are pretty small, so measuring 10 milligrams can be a little bit of a trick, especially if you've got like a metal or some highly densified material. Also, getting 10 milligrams can be really hard if you've got a really fluffy, lightweight material, because that might mean a lot of volume. But generally, just like with 10 degrees per minute, 10 milligrams is kind of our selected. So let's look, just like we did before, let's look at if I have more material or if I have less material than our recommended 10 milligrams. in this case, for the sake of hyperbole, I'm going to compare an ice cube to a glacier.
Okay.
A snowflake to a glacier. Ice cube maybe is a perfect sample. But we're gonna compare a snowflake to a glacier. So if I have a glacier, thermal gradients. The outside of the glacier maybe is like evaporating in the sun, and the inside is super duper cold. So we've got these thermal gradients through the glacier. Even if it gets really hot on the outside, the middle is never going to react until the whole outside has melted down. We are also going to see a slower transition. Similar to, or related, I guess, to that thermal gradient problem, is a slower transition. Icebergs exist at room temperature. Sometimes icebergs exist way above room temperature. Snowflakes, though, don't. And it's because just that quantity of thermal mass, and in this case it's cold mass, just you can't, there isn't enough heat to be absorbed to really make that transition happen. So the transition is going to happen a lot slower. If you're thinking on our time scale, right? Because it's happening slower, time and temperature are linked. So it's going to appear like it's happening at a higher temperature. It's going to start melting up here where it should start melting down here. And because that's happening in time, it appears as though it's also happening with relation to temperature. So that's going to throw off the onset of our graph there. If you have too little, we have sensitivity issues. It takes so little heat to melt a snowflake. Yep. And there's a possibility that our detector won't even notice that heat energy has been absorbed. So sensitivity issue there. As well as there's going to be a little bit more fluctuation. The difference between 1 and 2 milligrams is a really big percentage. That's a 100% increase. Where the difference between 10 milligrams and 11 milligrams, that's not a 100% increase, that's a 1% increase. 10% increase, sorry. Yep, I know how to math. Anyway, so we also have continuity isn't the word, it's like comparison or like uniformity, there we go. We'll have uniformity issues. So I'm not going to be able to compare this snowflake to that snowflake nearly as well because they are 100% mass different. So we have just decided that 10 milligrams is the value.
Awesome. Not
to say that less or more is a problem innately. We just have to be aware that there are going to be some trade-offs. Okay, just 2 more little things to talk about when we're thinking, like, prepping our sample. The gas in the atmosphere. There isn't like a regularly we choose this and then pros and cons list with this one. This is more just we do need to be aware of what the surrounding gas looks like. If I have a material like a metal that's going to oxidize and I run it really hot in air, I'm adding another reaction to my list of things that are going to happen over my temperature range. If I'm not worried about it, sure, use air. Maybe your polymer has no reactions with air and you're wanting to like heat and cool it in air because that's its final use will be in air. Then awesome. You also have to think about like humidity. Is there going to be humidity or not? All of these things are going to just add reactions Or if we choose a dry or inert gas, it's going to maybe remove reactions from the consideration. General rule of thumb is, how is your material going to be used, and use those parameters.
Okay.
Usually we will choose something inert like nitrogen or argon. But you can do, you can use other gases if you want oxidation, if you need like a passivation layer. If you're looking at like carbon uptake, so you're like, yeah, this thing is going to create, it's going to like bring in carbon. There's a potential that that has some sort of endothermic or exothermic if bonds are being created, not just like absorption. But just keeping aware that those interactions, these other gas interactions here, can change future reactions to your material. As an example, iron melts. So many notifications. The temperature of melting for iron is 1538 degrees Celsius. The temperature for melting for a simple FeO is 1377 degrees Celsius. So you can see we've lost about 200 degrees Celsius just by getting FeO, Fe2O3, FeO2. Those are going to have different melting temperatures themselves.
Right.
So just be aware of what atmosphere it's in. And one very last final consideration: supercooling or superheating. Have you ever seen those videos where they, or even done it yourself, it's a fun experiment, where you put in a water bottle that's unopened into the freezer and you don't shake it, you don't do anything with it, and it gets to freezer temperature, but it's still liquid.
Yeah.
And then you like smack it on the table and it freezes completely. That is supercooling. It's the ability for a liquid to get much colder than its freezing temperature because it needs a nucleation site before it starts to form those, crystallization, those crystals for crystallization. Supercooling is a lot more common than superheating. There are not a lot of materials that will get hotter than their own temperature. Even in the example where we chucked an ice cube in our oven, the ice cube itself is still right around 0 Celsius, even though the surroundings are 400 Fahrenheit. I'm sorry, I'm mixing units. That's absolutely terrible of me. Because supercooling is more common and superheating is less common, we usually trust a heating cycle more than a cooling cycle. What that means is if I am interested in studying the melting temperature of a material from 0 degrees to 20 degrees Celsius, this is, room temperature here. Mm-hmm. When I put the material in, it's likely that I'm going to start here at 20 degrees Celsius. I'm going to have to take the instrument down. We'll do it this way. And I'm going to see that freezing occur, at whatever temperature this happens. 0 was a bad example, but let's say I have something that freezes, at like 10 degrees Celsius here. So I am first going to cool down. Then, and we will use another color, I am going to turn the temperature around and I'm going to heat the sample and I'm going to see its melt. I trust the melt more than I trust the cooling cycle. Does that make sense?
Yeah.
And the reason for that is because there is a good possibility that we are going to get super cooling on this black line here, and that this onset value is going to be incorrect.
Gotcha.
Where it's maybe possible that this onset value as I'm moving this direction is going to be maybe more correct. I have drawn that poorly, so I am going to redraw it for the sake of like clarity. It would be something more like this, where we've got, no one answers that phone, I don't know, where we've got the T of crystallization there, versus here we've got the T of melt. And I trust that T melt value better than I trust that T crystallization value because of supercooling. Does that make sense?
Yeah.
Okay. Things that use DSC in like 2 minutes. Polymers for TG, for melt, for polymerization, especially things that are heat polymerized. We can do resins for like curing. That's usually endothermic or exothermic. We can do metals or salt or whatever else for melt. Sometimes we'll do liquids for like evaporation temperature. Basically, if you can fit it into that crucible, you're going to be able to do well with it. Our DSC does not have the ability to retain gases particularly well, so we don't usually run like gases cooling them down. And for us, it is not a repeatable reaction to evaporate something, so I can't heat, cool.
Right.
But some DSCs you can, just ours isn't really set up for that. It's useful across the board. If you care about the thermal properties of your material, you're gonna run DSC. It's one of those things that is really like basic characterization.